Good morning. I'm Spot on Weather meteorologist Matthew Euler, and today I wanted to put together a special video. Now that we're in the month of September, we're heading towards fall. In fact, we're already in meteorological fall, which started on September 1st. I wanted to really delve into winter season conundrums, or dilemmas, if you want to call it that. There's a lot of factors that go into winter weather considerations, really, as far as forecasting goes. So let's go right into it. We've got a full plate today to discuss and talk about. All right, so we'll go ahead and start off with an overview. An overview in that many teleconnections impact the sensible weather, whether that be temperature and precipitation patterns across the U.S. in the winter season. That's a plain fact right there. Now, what happens with the global circulation really matters and makes a big difference in what we see in the United States during the winter season. For example, in the Pacific, as well, even outside of the Pacific in the higher latitudes, that makes a big difference in what type of weather we see, especially in regard to temperatures and the storm track during the winter season. The jet stream configuration which guides those storms. Now, the Pacific versus the Atlantic teleconnections, there's many to discuss, and we'll delve into that today. We'll talk about El Nino and La Nina, which is one of the more infamous teleconnections you hear a lot about, especially in the news. In addition, we'll talk about stuff like the North Atlantic Oscillation, or the NAO. And there's competing factors here at work. There's competing influences between these teleconnections oftentimes, and that results in what's known as constructive or destructive interference, and I will get into that in a little bit. We'll go more in depth on the differences between those constructive and destructive interferences. And overall, it's not as simple as it appears. For example, there's no two teleconnections that are exactly alike from year to year. For example, there's no guarantee that a La Nina winter will completely behave like a La Nina winter. We had an El Nino winter a few winters ago, and I'll show you what a typical El Nino winter looks like as far as the atmospheric circulation here in a bit. But it definitely did not behave like an El Nino winter whatsoever. It actually behaved opposite as far as the sensible weather effects in the United States. So it's not as simple as it appears. This is a very complex topic, but one that's very good in helping us to perhaps predict the upcoming winter weather season. The Pacific factors, being that we live in the mid-latitudes between the latitudes of 30 and 60 degrees north in the United States, these Pacific factors or teleconnections, they really play a significant role in the U.S.'s weather in the winter. Due to the fact that, within the mid-latitudes, we are dominated by the prevailing westerly wind belt, in which systems generally move from west to east. So when I look out towards the west, towards the Pacific Ocean, that has a huge bearing on what type of weather impacts the United States. The configuration of the polar front jet stream upstream over the Pacific really helps to set up downstream effects, such as, for example, a positive versus a negative PDO or Pacific Decadal Oscillation. The winds aloft over the equatorial stratosphere also matter. These downward propagating easterly and westerly wind regimes that set up is known as a Quasi-Biennial Oscillation, or QBO. Those come into play as well. And of course, the well-known El Nino versus La Nina, the water temperature anomalies, the equatorial eastern Pacific, specifically in the Nino 3.4 region, and I'll show you where exactly that is here in a bit. Additionally, we talk about the Madden Julian oscillation, the MJO phases, as well as the PNA pattern, that Pacific North America pattern, and the Eastern Pacific Oscillation, or the EPO. All of this matters in determining what type of winter season we're actually going to see. What's the temperature pattern going to look like? Is it going to be a very cold winter versus a very warm winter? Is it going to be a near average winter as far as temperatures go? What about the precipitation patterns, the storm tracks? There's something out in the western U.S. during El Nino years that typically occurs that's known as the Pineapple Express, where you get a very active subtropical jet stream transporting a lot of moisture into places like California. These large little plumes of moisture are known as atmospheric rivers. Those are other examples. For today's agenda, we are going to go over these various winter factors, or how it develops into these conundrums. We're going to talk about the Pacific Decadal Oscillation, or PDO, the Quasi-Biennial Oscillation, or the QBO, the El Nino Southern Oscillation, which I just abbreviated as ENSO, the Madden Julian Oscillation, the MJO, the Pacific North American PNA pattern. We'll look at the Eastern Pacific Oscillation, or EPO. Additionally, the Arctic Oscillation, the AO, the North Atlantic Oscillation, the NAO, the Stratospheric Polar Vortex, which plays a huge role from the higher latitudes in the Arctic, and then solar activity, and I'll briefly cover constructive and destructive feedback. So let's start things off with a discussion of the Pacific Decadal Oscillation, or it's known as the PDO. This is defined as a warm or a cold phase, as defined by these ocean temperature anomalies, these departures from normal in the ocean, which makes a huge difference in our weather in the United States downstream from the Pacific Ocean. So you get these large ocean temperature anomalies or departures from normal in the Northeast and tropical Pacific Ocean. Now there's two phases to the PDO. There's a positive or warm phase, and there's a negative and cold phase. Okay, so the positive warm phase basically occurs when those sea surface temperatures are anomalously cool in the interior North Pacific and warm along the Pacific coast, and the sea level pressures are below average over the North Pacific as a whole, with a positive PDO, or the warm phase. With a negative cold phase PDO, this occurs when the sea surface temperatures are anomalously warm in the interior North Pacific and cool along the North American coast, with sea level pressures above normal. Okay, so a lot of things with the atmosphere and weather in general generally act opposite in direction. So if you get one phase that's positive, usually the negative phase, you have the completely opposite setup in the atmosphere. Let's take a look at the PDO. I wanted to mention that this PDO variation, the red spikes indicate the warmer phases and the blue spikes indicate the colder phases. This chart is courtesy of NOAA, and it goes well back into the 1800s, all the way up to about the year 2015. And I just wanted to show you how there's a cyclical variation to the warm positive phases and the cold negative phases of this PDO. So you'll see some years you have more of the negative PDO, other years the positive PDO. In addition, look at the magnitudes represented by the length of these spikes. And so we had a very strongly negative PDO back in January timeframe 1951, and a very strongly positive PDO back in the 1940s above a value of 3. So there's a cyclical variation of this. Here is what the phases actually look like. If I look at the water temperature, sea surface temperature anomalies, now these are in degrees Celsius, the scale's at the bottom there. Generally, you can see the image on the left shows a cool phase PDO. Right? We said the cool phase was also known as the negative phase, right? So the graphic on the left, you notice how the warmer water temperatures are over the Pacific Ocean further away from the U.S. coast, the West Coast, and the colder temperatures are along the West Coast with that graphic on the left with the cool phase. Now, the warm positive phase, you have a flip-flop of these sea surface temperature anomalies, where you get the warmer water temperatures well above normal from the Gulf of Alaska off the west coast of Canada down to off the west coast of the United States. And the cooler pool of water now is situated over the open waters, basically between Japan and the United States. So here's your main differences between these. Now, if you combine sometimes these teleconnections, if you look at the graphic on the left where I have a with the cooler water, right, that's going to be more of a warm phase positive PDO. And I combine that with a positive PNA pattern. look what happens to your jet stream. Your jet stream is represented on the left there by that white arrow, that thicker white arrow. So you see I have troughing off the west coast of the United States, generally over the below normal sea surface temperatures. And then I have this huge ridge immediately over western Canada and the western U.S., generally associated with warmer than normal temperatures and much greater than normal atmospheric heights. And then I have a downstream trough into the southeastern U.S., a lot of cooler air that's pouring into the base of that trough. So we can also combine teleconnections, and I'll get into the PNA here in a few moments, but I just wanted to show you what that can look like. If you look at the years, the upper right-hand graphic, the years that have a negative PDO versus the graphic on the upper right, there's a positive PDO temperature correlations, just showing you the difference. The yellows and the oranges represent above normal temperatures, while the blue and the purple shading is below normal. So during a negative PDO phase, that typically correlates to above normal temperatures from the southeast all the way up to New England, up to the mid-Atlantic to New England during negative PDO phases, whereas the positive PDO phase there in the upper right correlates to below normal temperatures across the eastern United States. So it's a flip-flop with the pattern, and that's where these teleconnections come into play. They alter the overall jet stream configuration, which leads to either warmer or colder than normal winters. If you look at the bottom right graphic, I'm showing you some examples from November 2016, and then a year later, November 2017. And these are sea surface temperature anomalies over the northern Pacific Ocean. And you can see on the left, I have cooler than normal water, which is situated over the Pacific, the open waters of the Pacific. And then a year later, November 2017, it completely flips around, where now I have above normal water temperatures or sea surface temperatures over the northern Pacific. So these things can also flip from one winter to the next winter. Now let's move into a discussion on the Quasi-Biennial Oscillation, or the QBO. Now this dominates the variability of the equatorial stratosphere, the overall winds in the stratosphere, generally from 16 to 50 kilometers, usually within 15 degrees of the equator, either side of it. And it's as seen as downward propagating easterly and westerly wind regimes with a variable period, generally averaging approximately about 28 months, just over 2 years. Through extratropical wave propagation, the QBO has an effect on the breakdown and is connected to the wintertime stratospheric polar vortices, that stratospheric polar vortex, which we'll talk about in a bit. Now there's two phases to the QBO. There's the east or negative phase and the west positive phase. And so just wanted to kind of briefly cover that. If you look at the bottom right-hand graphic there, you'll notice how this flip-flops these stratospheric winds above the equator between 16 and 50 kilometers from year to year. If you look at the graphic on the bottom right, that very far left globe, in January 2009, we had a westerly QBO, or a positive QBO. In April 2010, just not even a year or just over a year later, we had a switch to an easterly QBO, where the winds were mostly easterly in the stratosphere above the equatorial areas. And then it switched back in May of 2011 to a westerly QBO. So these things can change over time, again, just like I stressed with the PDO. Here's some examples of QBO and winter temperature trends for the United States, and this is why these teleconnections really matter. If you look at, we have points A through D on the left. At point A, we have a negative QBO, which, again, that would correlate to easterly winds in the stratosphere over the equatorial areas. With a negative and trending more negative, we generally have much colder temperatures across the Midwest, New England, even down to parts of the southern U.S., while it's much warmer than normal over Washington, Oregon, and California over the West Coast. In B, we have a negative trending QBO, and it's trending less negative, so it's not as negative, it's getting less negative, trending towards a neutral. You get a whole different temperature regime. You notice the yellow shading there indicates above normal temperatures. In cooler temperatures, the green shading out in the Pacific Northwest, and in the west into the Rockies as well. The other thing is at point C, where you get positive QBOs that are trending less positive. The white shading indicates near normal temperatures across the eastern U.S., And then you can see much warmer than normal temperatures across places like Montana, North Dakota, into parts of Idaho and the western U.S. And then lastly, at point D, you'll see a positive QBO trending more positive, which results in very warm winters across the Midwestern U.S., Minnesota, Wisconsin, Iowa, Illinois, Indiana, as well as down into parts of the South, Mississippi and Arkansas. And then you have the only cool air you'd have with this positive QBO trending even more positive, getting stronger on the positive side, is cooler green shadings there across Montana into Washington, parts of Oregon. So eastward or negative phases in summary of the QBO correspond to more sudden stratospheric warming events, a weaker Atlantic jet stream, and cold winters in the northern Europe and the eastern U.S. That's the eastward or negative phased QBO. A westward or positive phase QBO corresponds to mild winters in the eastern U.S., a stronger Atlantic jet stream with mild, wet, stormy winters in northern Europe, especially locations such as the UK, the United Kingdom. All right, now let's move on to El Nino. Now, this is very well known, very well known. We've heard this over and over in the media, in the press, on the news. This is an irregularly occurring and complex series of climatic changes affecting the equatorial Pacific region and beyond every few years. It is characterized by the appearance of unusually warm, nutrient-poor water off northern Peru, the country of Peru, and Ecuador, typically in late December. If you look at the bottom left-hand graphic, you'll notice that pinkish shading and the red shadings, that indicates well above normal water temperatures over the equatorial, eastern, into the central Pacific Ocean. Specifically, the way NOAA classifies El Nino is by looking at the water temperatures in the Nino 3.4 region, which you kind of see where that is, that rectangular area, the Nino 3.4 region, there in the equatorial, eastern, and central Pacific Ocean. So you can really get a look at how NOAA classifies El Nino. They look at the water temperature departures mainly in that Nino 3.4 region. Now, the opposite of El Nino is when things flip around, the atmospheric circulation in the Pacific completely changes, and you get below normal water temperatures from the equatorial eastern Pacific over into the equatorial central Pacific. This phenomenon is known as La Nina. It's an oceanic and atmospheric phenomenon that has colder, it's a colder counterpart of El Nino, and is characterized by unusually cool waters across the equatorial Pacific. If you look at the graphic here on this slide, you notice the blue shadings that indicates below normal water, which is extending just off the coast of South America, all the way just south of Hawaii, along equatorial areas into the central Pacific. Here are the circulation comparisons between El Nino and La Nina. And where these pools of warmer than normal or colder than normal water set up across the equatorial, eastern, to central Pacific really make a difference in the circulation patterns. For example, at the top with El Nino, the brown arrows indicate dry sinking air. The orangish shading, lighter brown shading indicates warmer than average water temperatures. And then the blue shading indicates cooler than normal water temperatures, okay? So with El Nino, you have sinking air motion generally over the western Atlantic Ocean and also sinking air motion over the western Pacific Ocean. And you generally have rising air motion over the eastern Pacific. With La Nina, it's the opposite. Now we have sinking air motion across the western, eastern Pacific Ocean and parts of Africa, and you have rising air motion with La Nina now in the western Pacific Ocean, and rising air motion across the tropical areas of the western Atlantic Ocean basin. And El Nino and La Nina play a huge role as far as tropical activity in the Atlantic basin. For example, during El Nino years, you typically have a more energized subtropical jet stream, increasing winds, with El Nino, and that tends to tear apart these thunderstorm complexes, these tropical easterly waves, and they really can't get organized because of this increased wind shear. In addition, you notice with El Nino, you have general sinking air motion across the western Atlantic Ocean basin. That's not favorable for tropical development because you want rising air motion. With La Nina, it's the opposite. La Nina favors a more active tropical or hurricane seasons in the North Atlantic Ocean basin because your tropical jet stream has weakened. It's not as strong, so the wind shear is much more relaxed. Wind shear being just a change in wind speed and direction with height. Those wind speeds with height with the winds are much less with La Nina. And you also have more favorable upward vertical motion with La Nina across the western North Atlantic Ocean basin. So again, with weather, there's always an opposite effect, right? El Nino to La Nina, another great example of this. For winter comparisons now, for El Nino winters versus La Nina winters, now look at the way your jet stream is setting up. With El Nino winters, you tend to have a more energized southern branch of the jet stream. That Pacific jet stream, lower latitudes, is more energized during El Nino winters. So you tend to have wetter weather, above normal precipitation from Southern California across the Gulf Coast states, Florida, slightly up the eastern seaboard there into the southern portion of the mid-Atlantic states. You tend to have drier conditions across the Ohio River Valley, and then warmer than normal temperatures in Alaska with El Nino winters, down through western into central Canada and overall Pacific Northwest and northern plain states. But the graphic on the right shows a La Nina winter, the opposite. Now that blue arrow indicates your polar front jet stream, and notice how it tends to form a ridge in the Gulf of Alaska, and then that dipping motion with colder than normal temperatures, that trough setting up from Montana into the Midwest specifically for La Nina winters. And you typically get wetter than normal weather across the Pacific Northwest during La Nina winters. Across the East Pacific, you get these blocking high pressure systems, which causes that huge upper ridge into the Gulf of Alaska. And then you also get drier conditions now across places that were wetter than normal during El Nino, places from Southern California to Texas, including Louisiana and parts of southern Mississippi, Alabama, into Georgia. And you tend to get warmer than normal weather as well, a warmer than normal winter across parts of Texas up through the mid-Atlantic states. So here's your main difference again between El Nino and La Nina. And what happens in the Pacific really does have a huge bearing on our weather in the United States. If you look at the natural variation of the El Nino Southern Oscillation, the ENSO, the red spikes indicate El Nino years, the blue spikes La Nina years, and there are different classifications to these from weak to moderate, strong to very strong. And you'll notice some of the strongest El Ninos on record were in the years 1982-83, that winter, 97-98 winter, and even the 2015-16 winter was up near a magnitude of 2 for a stronger El Nino. Now the La Nina years, if you look at the bottom there, some of the stronger La Nina years occurred there in 1973, 1976, just before, like 1988. See some of those blue spikes in the stronger territory for El Nino versus La Nina. So just wanted to show you the variation going back to 1950 of ENSO. Moving on now to a discussion on the Madden-Julian oscillation, the MJO. Now, this is a major fluctuation in tropical weather on weekly to monthly timescales. It's considered an intra-seasonal tropical climate variability. Now, MJO is an eastward moving pulse of clouds, rainfall that enhance convection, moving from west to east. Also, winds and pressure are associated with these pulses. Near the equator, that typically recurs on an order of every 30 to 60 days. They're divided into phases 1 through 8, corresponding to specific areas of enhanced convection. Now, these phases correlate to specific weather, different temperature and precipitation patterns across the United States. All right, so I want to show you on the graphic on the left an example of how these pulses of convection, enhanced rainfall, increased winds, and upward vertical motion, how they translate across the Pacific Ocean, okay, equatorial areas of the Pacific. So if you look at this graphic on the left, you'll notice week 1, the enhanced convection, the rising air motion, is generally located in the Indian Ocean. By weeks 2 and 3 there in the middle graphic on the left, you'll notice how it has shifted to the east. And now the enhanced area of rainfall and increased convection is actually located in the vicinity of Guam in the western Pacific Ocean. And by week 4 and 5, that same pulse has now translated eastward over the open waters of the western Pacific, getting into the central Pacific Ocean, closer to the international date line at 180 degrees west longitude. So these things, these MJO pulses move from the west to the east, the equatorial Pacific, the Indian Ocean into the Pacific, and you can see how these upward vertical motion areas move over time. Now, if you look at the graphic on the right, just showing you the upward and downward vertical motion associated with this overall MJO phase, where you have the brown arrow indicating suppressed convection, sunny and dry conditions. Whenever the air sinks in the atmosphere, it tends to dry out and warm. So you get a lot of fair weather in areas where you see the downward motion, the brown arrow. But then you have this low-level convergence that goes into this upward motion area to the west of the suppressed convection area. So it's a cycle of suppressed versus upward motion, suppressed versus upward directed enhanced convection. And you kind of see how the flow goes from the low levels of the atmosphere over the equatorial Pacific, in this case on the right, all the way up to around the jet stream level, and then spreads out and the air diverges above these areas of low-level convergence or enhanced convection. Globally, MJO plays a huge role especially in the winter season. Also very important in tropical cyclone forecasting. Certain phases of MJO equate to more active tropical conditions compared to other phases. Certain phases of the MJO in winter for the United States weather, they basically result or correspond to times of warmer or colder than normal weather, or wetter or drier areas times of weather. So just in general, I want to show you what this looks like. This looks like, we have atmospheric rivers indicated by the blue shading I mentioned earlier. Just this large plume of tropical moisture, sometimes known as a pineapple express, directly from Hawaii into the west coast of the United States, which can result in extensive flooding. You get, in this case, we have the MJO enhanced convection phase, generally in the vicinity of just to the east of India, translating towards the east. In general, we have the storm track denoted by that dark black arrow over the North Pacific, the central North Pacific. So there's a lot of changes that occur due to the MJO. It has a huge bearing on the weather of the United States, especially if it gains some fairly large amplitude. I really like this graphic on the left that just shows you where the enhanced convection occurs with the various phases of the MJO. MJO ranges from phases 1 to 8, and you'll notice wherever that number is. So for example, number 2 on this graphic on the left, that would indicate that the enhanced convection is occurring generally in the equatorial areas just south of India. But if I go to phase 8, now my enhanced convection is closer to the international date line, 180 degrees west longitude. So if you look at this, it's a great example to show you phases 1 through 8 and where the enhanced convection is occurring. The graphic on the right, I really wanted to hone in on the fact that these phases, what they mean for our temperatures, as well as our precipitation patterns, they change. I'm showing you a temperature composite, which is readily available on the Climate Prediction Center website. If you click on the MJO link on their main homepage, it'll take you to temperature composites. Phases 1 through 8 for December, January, and February is what I'm showing you. Those phases are going to be different throughout the course of the year. So, for example, the blue shading on the right-hand graphic here shows below normal temperatures, and the orange shading above normal temperatures. All right. Now, during the wintertime, phases 8, 1, and 2 are associated with colder than normal weather, generally from the Midwest to the East Coast. Those phases 8, 1, and 2 may actually not equate to the same temperature departures, let's say, in the middle of summer. So it changes. These temperature composites change from month to month and season to season. They're never exactly the same. I'm showing you the wintertime, December through February graphic on the right. Since my main focus of today's video is on winter weather. And phases 3, 4, you get into phases 5 and 6 in the wintertime, December, January, and February, you're going to have much above normal temperatures, the orange shading there, from the Midwest to the East Coast. This is a great graphic just kind of breaks down the different phases of the MJO and what kind of weather we see in the United States. So if you look to the right of that solid black line, in phases 4, 5, 6, and 7 of the MJO, you generally associate that with warmer winter phases, get above normal temperatures across the eastern U.S., less tropical impact phases as well during hurricane season if you're in phases 4 through 7. On the other hand, phases 8 through 3 in the winter generally equate to colder temperature phases as well as spring. And you also get higher hurricane impact phases for the North Atlantic Ocean when you're in phases 8 through 3 during the hurricane season. One other note I wanted to make, if you correlate these areas of this diagram, right, and I talk about this on my teleconnection discussions weekly during the cool time of year, the winter season specifically. Phase 5, for example, that would be convection over Australia, right? If you look at the graphic on the left. What about phase 1? Phase 1 would be convection generally in the location of Madagascar to the east side of South Africa. So you can equate to where the MJO is forecast to be and where those enhanced areas of convection are occurring rather readily. And this is great. Again, this is a great summary of the MJO and how it impacts U.S. weather. Now let's move on to the Pacific North American pattern, PNA pattern. This is one of the most prominent modes of low-frequency variability in the Northern Hemisphere, extratropics. When I say extratropics, I mean outside the tropical areas. The positive phase of the PNA pattern features above-average heights, upper-level heights in the vicinity of Hawaii and over the Intermountain region of North America, and below-average heights downstream, south of the Aleutian Islands, especially downstream over the southeastern U.S. The PNA pattern is associated with strong fluctuations or changes in strength and location of the East Asian jet stream. The positive phase is associated with enhanced East Asian jet stream, the negative phase with a westward retraction of that jet stream toward Asia. Blocking activity over the high latitudes of the North Pacific occurs, and you get a strong split flow configuration of the jet stream over the North Central Pacific. So again, we're talking about the Pacific Ocean. We're talking about what's going on with these teleconnection patterns upstream in the wintertime. The positive phase is generally associated with above average temperatures, with those above average heights over the western Canada and the extreme western U.S. areas, and below average temperatures and heights across the south central and southeastern U.S. The graphic on the left just showing you 500 millibar or 18,000 foot height, upper level height anomalies, departures from normal during a positive PNA. With a positive PNA, we get this upper level ridge to develop over western Canada and the western U.S. and a downstream trough, generally from the Midwest to the southeast coast. With a positive PNA, look at the temperature anomalies on the right. With that type of pattern, again, well below average temperatures extending from New England down into the mid-Atlantic states, with above average temperatures observed over the western U.S. A negative phase of the PNA pattern, you get an association with below average temperatures over the western U.S. and above average temperatures across the eastern U.S. with a negative phase PNA. Now, look at the bottom diagrams here. They show now a trough and below average heights over western U.S. and western Canada, and you get above average heights and a ridge over the eastern U.S. and much warmer temperatures there in the bottom right are associated with the upper level ridge from the southeast to the mid-Atlantic states, and much below average temperatures over the western U.S. and Canada. And then we'll talk a little bit about the East Pacific Oscillation, and I think I'm then going to split this video into two parts. This is part one. And just for time's sake, I'm going to split it down, kind of like try to split it up here. For the Eastern Pacific Oscillation, also known as EPO, this is a variation in the atmospheric flow pattern across the Eastern Pacific as well as Alaska. And when the EPO is in this positive phase, you get mild Pacific air that flows straight into the west coast of North America, resulting in a warm and dry weather pattern across most of the central and eastern U.S. and southern Canada. So when you get a very strongly positive EPO, you got a much more amplified, well, I won't say amplified, but stronger west-to-east flow of that Pacific jet stream, which generally tends to flood the North American continent with more maritime polar air. And the jet stream really doesn't have many dips in it or many troughs to direct much colder air from Canada down into the lower 48. Instead, again, the U.S. mostly has a maritime polar or Pacific air mass influencing conditions from the west to the east coast with a positive EPO. Now, the negative EPO, on the other hand, you get a much more amplified jet stream where you get this ridge in the upper levels of the atmosphere over the eastern Pacific off the U.S. west coast, with Alaska being warmer. Cold air then, as that ridge builds into the higher latitudes into western Canada and Alaska, tends to then dislodge much colder air on the front side of that ridge into a trough-like pattern across the Midwest and East Coast, with much cooler air, colder than normal winter weather, into the central and eastern U.S. when the EPO is negative. Here's a couple examples of the patterns associated with both a positive and a negative EPO pattern. The graphic on the left shows a positive phase of the EPO. We got a fastly moving, highly zonal west to east jet stream with a positive EPO pattern, which generally what happens when you have a highly zonal west to east jet stream is, again, the coldest air stays well to the north, and you get this mild flow of Pacific air from coast to coast. In addition, with a flatter jet stream like this, a highly zonal jet stream from west to east, you generally get faster moving, weaker upper level disturbances or storm systems that move through the pattern. The graphic on the right shows a negative EPO pattern, and now we got a much more highly amplified jet stream where we get this huge Alaskan ridge, and that tends to dislodge much colder air. As that ridge moves to higher latitudes, it dislodges colder air on its front side down into the lower 48. And look at the bottom right-hand graphic there. You get much colder than normal weather across the United States as a whole, and well above normal temperatures across Alaska with a negative EPO pattern. And you also get much more intense storms or cyclogenesis when you get this kind of jet stream configuration where you get a deeper long wave trough. You get these disturbances, these short wave troughs rotating through the long wave pattern, and that really kicks off a scenario where you get much larger temperature contrasts, and generally those larger temperature contrasts energize the jet stream and result in a lot stronger storm systems with a negative EPO pattern. All right, I think I'm going to end right there, Arctic oscillation. I'm going to go back and I'm going to cut this into two parts. We're sitting at 37 minutes now, so I will be back in a moment for part 2.